All right, good morning, everybody. Welcome back to Galois Theory Appetite. Plan for today is we're going to talk more about field extensions. This time, proving a couple properties of field extensions and start talking about what relationship does field extensions have to polynomials and irreducibility of polynomials.
I love that.
I do too. Office hours. I got to cancel my afternoon office hour. Why? So, those of you who don't know, we currently have a job candidate on campus, Dr. Oliver Sarang, who's interviewing to become a second computer scientist in our department.
Oh,
Yay!
And he's doing his teaching demo at 1.
phenomenal.
And I want to be there for that. And I'd rather be there for that than talking to you. So, no office hours this afternoon.
I'm just trying to Darn it, I have too much to do, so I cannot be there at 1.
That's so sad.
It's gonna be a very full classroom.
Yeah, it's going to be, I don't know how much, I don't know if this one's super open to the public because it's for an actual class of, anyways, I'll have my usual office hours tomorrow or Thursday, Friday though. Homework. I'm going to post a homework 5. It'll be due, I'll probably post it tomorrow or Thursday sometime. It'll be due Thursday next week. Quite. And it'll be looking at some of these field extension and whatchamacallits. Don't forget, you all have a homework set due today. This last week has been one of the busiest of my life. Not really, but extremely busy week. So no, I don't have homework days yet. Any questions or comments before we get started for today? James?
What's the joke of the day?
All right. So, you all know good old Rene Descartes, right? Well, a horse walked into a bar.
Oh,
The horse sits down at the bar, bartender gives him a drink and says, "Hey, you know what, horse? You're in here an awful lot. Think you might be an alcoholic?" Horse thinks about that statement for a second and says, "I don't think that I am," and promptly vanishes because he is not. Ha! You all thought that was going to be a joke about Descartes, but I didn't want to put Descartes before talking about the
there you
horse. All right, and with that, let's do some field extensions. So last time, we defined what it means to have a field extension, where basically L over K is a field extension if K is a subfield of L. Technically, we said it doesn't have to be a subfield of L, it just has to be isomorphic to some subfield of L, meaning you have to have a one-to-one homomorphism from K to L. But practically speaking, we're just going to assume K is a subfield of L in pretty much every case. We also talked about how you can, given any field extension, L over K, you can make L into a K vector space, where the vectors are elements in L, your scalars are elements in K. You multiply a scalar by a vector by just doing normal multiplication in L. You add vectors by just adding elements in L using the field addition. And we said that the degree of the field extension, L over K, is defined to just be what's the dimension of K as an L as a K vector space. Holy moly. So in other words, if L is a K vector space, L has to have a basis, because any vector space has a basis. Property from linear algebra, any two bases for a vector space have to have the same number of basis vectors. The dimension of your vector space is the number of vectors in any basis. And so whatever the dimension of L is as a K vector space, we're going to call the degree of the field extension. So last time, we looked at a couple examples, starting with, for instance, the complex numbers over the real numbers. And does anybody remember what we said the degree of that extension was? PCO.
It's 2.
It's 2. Yeah, we said that the dimension of,
C factorial.
it's what?
As you wrote C factorial.
Well, I tried to write a colon and it didn't work so well. The dimension of the complex numbers as a real vector space is going to be 2, as C has what as a basis? Lincoln? Are you over there? I'm not kidding. No, I don't, forget I asked that.
1 pi I. Those two.
That?
Yeah, that works.
I don't know what, is that what you were trying to say?
Yeah.
That's what you're saying now. Yeah, that is a basis of that as a real vector space. Why? Because any element in the complex numbers can be written as a linear combination of 1 and pi I. So this is a set that spans the complex numbers, because any complex number can be written as real number times 1 plus real number times pi I. And it's a linearly independent set, which when you have two elements, linearly independent just means neither is a scalar multiple of the other. And there is no real number you can multiply 1 by to get pi I, and vice versa. So this is a linearly independent spanning set for the complex numbers as a real vector space. Has two elements, and so we get 2. We also talked about last time, what's the dimension of, what's the degree of the field extension R over Q? In other words, what's the dimension of the real numbers as a rational vector space? We said that was infinity because there's no nice easy way to form a basis for R, just where if your scalars are only allowed to be rational. Your basis would have to include things like pi, pi squared, pi cubed, pi to the 4th, pi to the 5th, etc., etc. Automatically given you it's infinitely many. So let's look at another one now. Let's look at this one. Q joined, let's do cube root of 2. One more example before we start looking at proving some properties. So first of all, what's this?
It's not a quotient group. It's
Very good.
it's a
You're
rational.
making progress.
Thank you. It's a rational number plus another rational number times the cube root of 2. Any rational number that's in cube.
So a plus b cube root of 2, where a and b are what?
A and B are going to be elements in cube.
Okay, sounds good. So let me ask you this, Parker.
Yeah.
Is this closed under addition?
Um.
You add two things this form together, you get something of this form?
I would say so.
Yeah, I would too.
Yeah.
Hey Isaac, if you multiply two elements of this form together, do you necessarily get something of this form?
I don't think so. I think you'll get, don't you have to do, since it's a cube root, wouldn't you need another one that's like the cube root squared?
You do indeed. Problem with what you gave, Parker, is it's not closed under multiplication.
You have to get to the point where it loops around on itself.
Yeah. Because technically, you could take cube root of 2 times cube root of 2, and cube root of 2 squared cannot be written in the form rational number plus rational number times cube root of 2. It's not exactly, it's not trivial to actually prove that, but that turns out to be the case.
I got close.
You got 2/3 of the way there, 66 and 2/3%. That gets you a D. Good job.
Oh, wait. No, don't do this to me.
Yeah. Whenever you see this notation, we're going to see a lot more of this going forward. Think polynomials of Q polynomials of cube root of 2. So like big Q of x, but replace all your x's with cube root of 2's.
Which is around.
But once you get to cube root of 2 cubed, then you just get a rational number, namely 2, so it loops back around. So that's a field extension. This is a field that properly contains Q. So what's the degree of the field extension? In other words, if we were to form a basis for this ring right here, for this set right here, how many vectors would be in said basis, Emily Rose?
3?
3.
I think 3.
Give me a basis then.
1 plus the cube root of 2 plus 2 to the 2/3.
That's 1. Oh, did you mean commas instead of pluses?
Oh my god, I said pluses.
That is.
Okay,
that
well
is-
no, let's go with pluses then. And the other one is cube root of 2 plus 2/3, 2 to the 2/3, and the other one is 2
Nope,
to the
I like
2/3.
this one.
You almost pulled a Lincoln Raisin.
So that turns out that is going to form a basis for cube adjoint cube root of 2. Why? Because this is a linearly independent set. Showing this is linearly independent is non-trivial. Particularly, showing these two are linearly independent from each other is, I mean, that's just immediate as cube root of 2 is irrational. Oh, you know how to show that cube root of 2 is irrational? This is a fun proof. Eleanor, you said you like proofs by contradiction, right? So assume cube root of 2 is rational. Then we're going to cube both sides. Then we're going to multiply both sides by q cubed to get p cubed is equal to 2q cubed, which is equal to q cubed plus q cubed, and that violates Fermat's last theorem.
What?
Oh!
So you can use Fermat's last theorem to prove cube root of 2 is irrational. In the same way that you can cut a stick of butter using a chainsaw. As in you are using some extremely heavy-duty mathematical machinery to prove something relatively straightforward. But it does work as a proof.
It's short too.
Say what?
It's a short proof too.
Yeah, it's a pretty short proof as well.
What's he assumed short proof? It's like a
I mean, once you've assumed, you know, this thing that
It's
took
like
like
chainsaw.
hundreds and hundreds of years and hundreds of papers, etc. to prove.
A chainsaw will swiftly cut butter. Yeah.
Yeah, exactly. Or like,
The question is how much butter you'll have left.
oh, it's a little bit chilly in this room. How about we set everything on fire?
I like that.
So that's how you can prove cube root of 2 is irrational, just as a fun aside. Proving cube root of 2 squared can't be written as a linear combination of these. A little bit trickier, but we're gonna prove that in the next packet. What should be a little easier to see, I hope, is that this is a spanning set for this, and that literally the way we wrote out this set is it's a set of everything of the form a times 1 plus b times cube root of 2 plus c times cube root of 2 squared. A, b, and c come from our field of scalars, namely q. Literally, from the way we wrote out this set, we know that this is going to be a spanning set. And that's going to give us a degree 3 extension.
Why does this feel vaguely similar to something mod 3?
I don't know. Because you've been working with the number 3 lately. And because there are deep hidden secret underlying connections to Z mod 3. As in perhaps the group of permutations of the roots of the minimal polynomial of this field extension is isomorphic to Z mod 3.
I like this.
Again, spoilers for like a month from now. But if this feels like Z mod 3, you're right.
I mean, it's like if you multiply cube root of by itself, you don't get 1, and if you multiply 2/3 2, you also don't get 1. It kind of acts like a mod 3 anyway.
Yeah, it sort of behaves a lot like third roots of unity. If you've seen those, like 1 e to the 2 pi I over 3, e to the 4 pi I over 3. That's a group that is those form a group under multiplication that is isomorphic to Z mod 3.
Right.
I don't know. I'm giving lots of spoilers now for stuff that's coming down the line, but there is connections. Is what I want your takeaway to be.
Even in
My favorite spoiler was when you spoiled us proving Fermat's last theorem.
What?
What? Oh, we're not proving Fermat's last theorem in this class. I assure you. I would need the rest of the semester, and then about 30 more semesters to prove that. I would need about that much time to understand the proof of Fermat's last theorem, I think. Alright, so question.
We could do 7%.
Pete, can you give me an extension of the rational numbers? A field extension whose degree is 113.
Wait.
You're scaring me.
Nothing comes to mind immediately.
Matthew?
I was gonna take a shot in the dark.
Alright, let's hear your shot in the dark.
113th root of 2.
I think you mean to say you adjoined
Okay.
Oh.
Technicality there.
Is that what you were going to do?
Yeah.
That's what I was
113th root of 2.
I was going to the
And yes, that
113th root of-
And yes, that would work.
Alright.
For similar reasons. For similar reasons, actually.
Now, what about the 113th?
You can form a-
113?
Shut up. You can form a base. You can form a basis by taking 113th root of 2, 113th root of 2 squared, thing cubed, thing to the 4th, dot dot dot, thing to the 112th power. And that would be not easy to prove without stuff we're going to do. It's not easy at all to prove that that's a linearly independent set, but proving that it's a spanning set for this ring would not be so bad.
Does C automatically multiply it by 2?
Holy smokes, I'm missing a line there. I'm sorry. What did you say?
Does C, like the imaginary, does it automatically multiply everything by 2 because they have to have an I version for all of it?
I don't know what you mean by multiply
Like
everything
the
by 2.
total number, so like, if it was like,
It means,
Like if this-
Imaginary, yeah.
if this was C,
Oh, so if you had like
like C of 113th root of 2.
C adjoin.
That's just.
so that's just so that would be 1 because C adjoined 113th
Oh,
root of 2
yeah,
is
yeah,
just
yeah.
C.
Yeah, I see what you're saying.
But if you were to do something like
If you added
But what
to
if
the, do we
it's-
have there another set of brackets with I?
yeah, can
Uh,
we double adjoin?
Oh,
you can. And in fact we're gonna be doing that.
Or, I was saying another set of brackets, because
Like a separate adjoin. Yeah.
Hint, putting the comma and doing it in a single set of brackets gives the same thing as this.
Oh, there was a
Didn't see
comma
the-
there?
There was a
I didn't see
comma.
the
Oh, I didn't see
comma.
Oh yeah, sorry.
Okay.
Yeah, we'll be doing that later this class, by the end of today, in fact. We'll be doing something like that. Yes. So you could do a similar sort of argument to this to prove that for any natural number n, there exists an extension of q of degree n. Also, from the R example we see last time, you can also have extensions of q of degree infinity as well.
I also noticed that we fixed, I believe 113 is a prime number, isn't it?
Is it?
Is it prime?
I don't actually know.
Oh, wait, well then, would it work if you didn't choose a prime number? Like if you did
Well, you
for,
just said for all ends.
I mean for
I
all,
said
yeah,
for all n.
yeah, but that doesn't mean we can generalize that process to all n.
Turns out it does, even if it is.
Oh, it does, okay, well
Tells
that's,
you use
You can like,
one,
well, cause if
isn't
you
it?
use,
well, because then if you do the multiplication, it's just,
Yeah, well, the group that Eleanor was thinking about may not be cyclic
Yeah.
if P is not prime, but it would still give you
it's still so,
or it might not have a unique generator, let me say, if it is not
okay,
prime.
that's
but,
what I was thinking, that's what I was thinking about, yeah.
Let's prove some stuff. What do y'all say? Alright, first proof. If and only if. Turns out field extension has degree 1 if and only if L and K are the exact same. L equals K if and only if in other words, a degree 1 extension is no real extension at all, except in the trivial sense. And that you're not actually adding anything to K if you're extending it by a degree 1 extension.
Or what if they're isomorphic and not the same thing?
Nope.
But it has to be a
Equals.
subfield,
Okay.
because it has to be a subfield.
Oh, right.
Well, unless you want to go back to the original definition of field extension, where K doesn't have to be a subfield of L, K just has to be isomorphic to a subfield of L, then yes. Then you would place equals with the isomorphic.
And does that still hold?
That would still hold with the isomorphism thing. And in that case, you would actually get L is, or you would actually get K is equal to, or is isomorphic to exactly that subfield of L that you're using in constructing that thing. But for this definition of field extension, it's actually strict equality. Which does imply isomorphism, but not the other way around. So let's take a look. Two directions. Left to right's a little bit easier. We're going to suppose L equals K. And we need to show that we can find that if we treat L as a K vector space, or L as an L vector space in this case, because they're the same, that we can find a basis with one element in it.
Oh.
So, no matter what your field is, what's always going to be a basis for that field as for a vector space over itself? Isaac?
1.
You can just take one.
Like just multiply it.
Because literally anything in L is just going to be that thing times 1.
Yeah.
As any, let's say, element A and L can be uniquely written in the form A equals A times 1. In other words, there's a unique thing that goes in this blank here that makes blank times 1 equal to A. And that unique thing is just A.
Does this work for any unit in L?
Yeah. Yeah, because if you replace 1 with U, you could just say A equals AU inverse times U is a unique solution. So you don't necessarily have to choose one. One's just the easiest thing to choose. Hence, the dimension of the field extension L over K is equal to this, which is 1. So that's forward direction. That any vector space over anytime you take a field and you define it to be a vector space over itself, meaning your vectors and scalars are the same thing, you could just have set containing 1 and nothing else be a basis, because every element in L can be written as some scalar multiple of 1, namely itself times 1, and 1 is a linearly independent set. Why? Because 1 isn't 0, and any single element set that's not 0 is linearly independent. Questions, comments, concerns? Yeah, sure.
Why is 0 not linearly independent?
Because, why is this set not linearly independent? Because, linearly independent means there's the only solution to this equation would have to be, the only thing you could plug in this blank would have to be 0.
Oh,
If this was a linearly independent set, but it's not.
okay.
There's lots of things you could plug into this blank, in fact, literally anything.
Because it's impossible for it to be.
The only scalar you can multiply 0, there's lots of scalars you can multiply 0 by to get 0. Whereas if you contrast that with 1, looking at this, there's only a single thing you could plug in this blank that would make that happen.
So it needs to be something with no zero divisors.
Well, we're in a field.
We're over a field, so we're assuming integral domain, so we're assuming no 0 divisors, but yes, you're right. The fact that we have no 0 divisors is important for all of this.
And we have 1 and all those things.
Yes, well, yeah. Also, if we're not in a field, we don't necessarily have an element 1 or any units to work with. Which, thankfully, we're working over a field, so we have all the stuff that we get to use. Like the existence of 1 and the absence of 0 divisors, for instance. Alright, let's take a look at the backward direction. So backwards direction's a little more interesting. We're going to suppose that that the degree of the extension L over K is equal to 1. And we need to show that L and K are equal to each other. Since we're already assuming L over K is a field extension, we know K is a subset of L. Like that's kind of implied by this. So we really, in order to show equality, we just need to show every element in L is also in K. Because then we get both sets are included in the other and they must be equal. So what does it mean to say that the degree of the extension is 1? How does that give us something nice and practical that we can use? Isaac?
The basis should have one element.
Yeah, that means there exists a one element basis for L as a K vector space. So exists a basis. I'm going to call the one basis element. I'm just going to call it V for L as a K vector space. Question: where does V live?
In L?
When we talk about a basis for L as a K vector space, a basis has to be made up of vectors coming from the vector space. So here, V is an element of L. Thought I'd mention that because it's worth noting. We don't know if V is in K necessarily. If it is, we're done. 1 here, we didn't have. Is 1 here referring to something from L or from K?
Because they're
Well, L and K are equal. Let's say we didn't know. Let's say we didn't immediately assume L and K were equal. What would 1 be referring to? Actually, still both, because
We assumed that it was equal as like the starting.
well, that. But even if K is just a subset of as a subfield of L, they're still going to have the same multiplicative identity in order for one to be a subfield of the other. And yes, the fact that we started by assuming L equals K makes that very trivial question. All right, so we got a one element vector space, and our goal is going to be to prove that V has to be in K, because if we can prove that V is in K, we can use that to show that every element in L would have to also be in K, which would let us conclude that L equals K. So that's our goal. Prove V is an element of K. Well, since L is a field, there exists an element A and K, or actually not since L is a field, since this is a basis, I should say. There should exist some element A coming from our field of scalars, so that A times K is equal to 1. Why is that? Or, what am I doing? AV. I'm sorry. It's been a tiring class for several days, guys. So, if we're assuming that this is a basis for all elements in L, well, here's an element in L. If this is a basis, that means this is a spanning set, meaning every element in L, such as 1, should be able to be written as a linear combination of elements in this set. And what does it mean to take a linear combination of elements from a singleton set, a set with one element? It just means scalar multiples of that element. If this was like a V1 and V2, then we'd say there exist A and B such that AV1 plus BV2 is equal to 1. But since there's only a single element, you just need a single scalar. So if A times V is equal to 1, what does that tell us about the relationship between A and V? They're inverses of each other. So in other words, V has to be equal to A inverse. Which in turn implies that since A is an element of the field K, and V is the inverse of that, by the fact that K has to contain its own inverses in order to be a field. Any questions or comments relating to that? If you're the inverse of something in K, you must yourself be in K. Otherwise you'd get that A is an element in your field that doesn't have a multiplicative inverse. A would be an element of K that doesn't have a multiplicative inverse, and thus K would not. And no, we know that A is non-zero, because if A was 0, you would not get A times B equals 1. Alright, so we now know that our one basis element of V is going to be an actual element of K. So since V is an element of K, we know that any element of the form AV, where A is an element in K, also has to be in K. And that's just the closure of K under multiplication. Plus, since any, Seamus, I need a new variable name.
P.
Since any element P and L has to be some scalar multiple of V, that tells us, can be written in this form. That's going to tell us L has to be a subset of K. Why? Because we just showed that literally any single element in L, which can be written as scalar in K times this V. Any element in L has to be in K, thus L is a subset of K. Jonah?
So if we I guess thinking back to the first part, if we had L and K both be the trivial field, would the dimension then be 0 instead of K?
Trivial field still has to have one element in it.
Right, but I mean,
No, just one.
but ordinarily we wouldn't say that something has like.
Yeah, but it would still be a dimension one extension.
I mean, would you say that like the set that's just consists just of 0 is just of the 0 vector has dimension 1 in a vector space ordinarily? It would be.
No, you're right, it would be dimension 0. Alright, fine. We're assuming L and K are non-trivial for the purposes of this proof.
L or K is not true.
Well, if one is, the other is, so. Alright. Because technical definition of dimension, I don't want to get into it. So Isabel, we now know L is a subset of K, yeah. But we also know K is a subset of L because that's what it means for L to be a field extension of K, right? If K and L are both subsets of each other, what can we conclude?
They must be equal.
They must be equal. Excellent. Glad you remembered your discrete math. And so the only way for a field extension to be of degree 1 is if it's not an extension at all, and L and K are the exact same field. Again, relying on our kind of naive understanding of a field extension is just a smaller field living inside of a bigger field. Alright, so next thing I want to prove, we got a nice tower of multiplicativity. That's hard to say.
Whoa.
And that field extensions multiply together nicely.
This looks very.
It looks like potion fruit.
Oh boy.
Huh. It must be coincidence. So next theorem is going to say that if L over K and M over L are field extensions, meaning that K is a subset of L, is a subfield of L, which in turn is a subfield of M, then the degree of the extension M over L times the degree of the extension L over K is always going to be equal to the degree of the extension M over K.
So then back to the last point, we're going to want to define it as one actually instead of zero.
We should define it as one. That's just
Should define what as one?
What we were just saying for the trivial, because otherwise there's the problems here, right? Because then something times zero.
Assume all fields are non-trivial for the purposes of this class until I say otherwise. So, in other words, the degree of the extension M over L times the degree of the extension L over K is equal to the degree of the extension M over K. And before you ask Jonah, yes, this also works if either or both of these are infinite.
Okay.
I'm not going to prove that case, though. It does work if one of these things happens to be infinity,
Which just turns the whole thing into infinity.
essentially.
Okay.
What if they're different cardinalities of infinity?
Still works. Not getting into it, but it still works. I'm going to prove the finite case because finite case is messy enough. Alright, actually, let's do an example first. So, quick example. Andrew,
Yes.
what's the degree of this extension? We extend 2 by square root of 2.
2.
Yeah, it's going to be 2 because you get a basis consisting of 1 and square root of 2. But Andrew, answer me this. What's the degree? Oh, you don't know that notation yet.
Yeah, I was wondering.
Of this extension.
2.
Why?
Because you can find a basis, say 1 and square root of 3.
We know it's not 1 because these are not the same field. So it has to be at least 2.
Yeah.
And we know it can't be any greater than 2 because we can always form a spanning set for this as a Q adjoint root 2 vector space. So, so it's going to be 2. So what does that tell us? About that, Eleanor.
It's 4.
That means if you were to form a basis of take Q, take polynomials in Q over square root of 2 and square root of 3. So it's like you have like x's and y's that you can form polynomials of, but your x's are square root of 2's and your y's are square root of 3's. That's going to be a 4-dimensional vector space over Q. In fact, here's how you can form a basis.
1, root 2, root 3, root 6.
Yes. You would get a 4-dimensional degree extension. Any questions or comments about what this theorem is saying before we start trying to do a proof of it? Andrew?
No, I don't.
Okay. That looked very questioning in your face, though. Stop it.
I did have one, but I answered it, so.
Okay.
Well, if any of these equal each other, then you just get one of those as 1, and then you.
Well, yeah. If any of these are equal, then this becomes trivial.
Yeah.
Mhm.
And will still work very nicely.
Yes, trivial if we use the theorem that we just proved. So here's proof. I'm going to limit ourselves to the finite case. The book goes through the infinite case, and I just don't feel like it, if I'm being honest. So we're going to suppose that this is some finite number, this is some finite number, and then directly prove that this is the product of these things. So we're going to suppose that the degree of the extension m over L is equal to r, and the degree of the extension L over K is equal to S. So what does that mean? Well, that means we can construct bases of M as an L vector space with R vectors. So we can form a basis, call it M1 up through M sub R, for M as an L vector space. And another basis, we'll call it, what did I call it? V1 through Vs for L as a K vector space. Say what?
M and V.
M and V, what about M and V?
Nothing technically.
Gossip will use what it's thinking about.
All right, Isaac, tell me this. How can we then construct a basis for M as a K vector space?
So we would take, I think you just combine, over here we needed each of the ones in M, each Mi,
Mhm.
matched up with one of the V, with all of the V, I, or J.
Mhm.
So you'd have M1, V1, M1, V2, and so on, then M2, V1, and so on.
In other words, the claim is going to be that if you take all products of thing in this set, and if you take the Cartesian product of these two sets, that's going to form a basis for M as a K vector space. So I'll put claim, I did not write the straight line here. The set of all elements of the form M sub I, V sub J, where 1 less than or equal to I less than or equal to R, 1 less than or equal to J less than or equal to S, is a basis for M as a K vector space. So in other words, the set of all linear combinations of these things is going to give you literally every element in M. And also, these are all linearly independent, meaning if you have some polynomial of all of these that gives you 0, some linear equation involving all of these that gets 0. So if you have something like constant times m1 v1 plus constant times m1 v2 plus constant times ... plus constant times m sub r v sub s, and that comes out to 0, I claim that all of those constants would have to be 0, meaning this is a linearly independent set. So let's prove that. So we have two things we need to show here. We need to show that this set is linearly independent and that it spans M. Jackson, which one do you want to do first? Show that this is a spanning set for M, or show that it's a linearly independent set?
The independent set first.
Linearly independent. Okay, sounds good. Opposite order from how I did it in my notes. So to do that, like I said, we need to show that if we take some linear combination of all of these things and get 0, then the only possible way that can happen is if we're multiplying each of these by 0 individually and adding them together. So we're going to suppose, alright, brace yourself because we need doubly indexed subscripts here. B11 times M1 V1 plus ... plus B sub R1 M sub S V1. That should be B sub S1. Oh gosh, I've already screwed this up in my notes. Plus B sub 1S M1 VS. No, this should be, no, this was R. This is where I screwed up, and that should be R1. plus b sub rs m sub r v sub s is going to give us 0 for some b sub ij elements in K, in the set of scalars for this vector space we're making. What do we need to prove here in order to show that we have a linearly independent set? Lincoln?
Then all the B's are 0.
That all the BEs are 0, indeed. Well, so what I'm going to do is I'm going to take this equation right here, I'm going to regroup terms and say then 0 is equal to, and I'm going to regroup and factor out an m. So what I'm going to do is I'm going to combine all the terms that have an m1 in them with each other, etc., etc. Then I'll combine all the terms that have an m sub r in them and say 0 is equal to b11 v1 plus dot 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 plus b1s vs times n sub 1 plus b sub r 1 v1 plus dot 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 plus b sub rs vs times m sub s. So all I did is I just took these terms and regrouped them and then factored out an m sub I from the regrouped terms. So what does that tell us? That tells us we have a linear combination of these things that's giving us 0. And what do we know, Eleanor, from the fact that these are linearly independent? What does that tell us?
Is that the things before them have to be 0?
Bingo. What?
Not MS, MR.
Unless they're not Ms.
Yeah, that's true. Sorry, there's a lot of subscripts floating around here, so I'm going to probably miss a couple more, so help me catch those, please. So we can now say by linear independence of the m sub I, that's going to tell us that that's going to tell us that this equals 0, this equals 0, and all the coefficients in front of the m sub i's are going to give us 0. So that's going to tell us b11 v1 plus dot 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 plus b1s vs is equal to 0, dot dot dot, br1 v1 plus dot 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 plus brs vs equals 0. And that comes from the m sub I being linearly independent, which we know they are because they're forming a basis. But now what can we do with each of these equations? Same thing, but using that what is what?
The
B sub I are linearly independent.
Yeah, that tells us by linear independence. Now we're going to use of the v sub I, j, could use i's if we wanted to, of the v sub j's, b11 up through b1s are equal to 0, etc., etc., br1 up through b sub rs are 0. And we've proven linear independence of this set. We've shown that the only way you can take a linear combination of all of these terms to get 0 is if every single one of these coefficients comes out to 0. Quite. Well, it's not very nice. It's notationally very messy.
But it works out very nicely.
The book does it slightly differently. Instead of having a lot of symbols, the book uses two, like, double and triply index sums here, which is its own brand of scary.
Ooh.
Like summations inside of summations.
Oh, yeah.
Yeah.
No,
Much
this is
easier.
better.
I prefer it this
I
way.
kind of see how that would work.
It's shorter, but it's also like harder to like actually think about what does an individual thing look like.
Yeah.
I prefer it this way. Any questions or comments about the linear independence? Neato burrito. So what else do we need to show about this set in order to prove its basis?
Span.
Yeah, we need to show it spans. That it spans what? That it spans M, because we're claiming that this is a basis for M as a K-vector space. What else is this?
I thought you had some things.
You doing okay?
Dr. Gerstle,
Lydia, you doing okay? Glad to hear it. Yeah, what?
this is the first time that you've added an extra sheet of paper on the back end of a packet and I've actually used it.
How about that?
You've never used it?
No, I
See,
keep
I
thinking
didn't
I'm going
need
to.
it. Neither.
I keep thinking I'm going to every time there is one. I keep not using it. This time.
I
This
use it.
time.
I use it all.
So we need to show that any element in N can be written as a linear combination of these things, where scalars are allowed to be elements in K. Quiet! We're doing math. So we need to show that any element, if I take, we're gonna let little m be an element in big M, and we need to show that little m can be written as some scalar from K times M1V1 plus some scalar from K times M1V2 times some scalar from K times M1V3 times dot dot dot.
That's gross.
I'm gonna give the set a name so I can refer to it. We'll call the set
okay.
S. Say what? Suspicious? S for set, that there's no further reasoning behind that. Well, given M, we know we can write M as a linear combination of something. We can write M as a linear combination of these things, meaning we can write M as M A1M1 plus dot 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 plus ARMR, where the A's are elements of L. Not necessarily K, but L.
Oh, but we can write elements of L.
Aha!
As
As elements of K, as linear combinations of elements in K, and hey. Yeah, so that's what, so yeah, that's what we're gonna do. So we're gonna say, then for some, I'll call them A sub I elements in L, we can write N as being equal to A1 M1 plus dot 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 plus A sub R MR. R. As from the fact that, well, I'm not going to write this down, but that comes from the fact that this is a basis for M as an L vector space, meaning it needs to span M as an L vector space. As, oh, fine, I'll write it. As this is a spans M as an L vector space. And then for each A sub I, there exists B sub ij coming from K, such that A sub I is equal to B sub I1 V1 plus dot 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 plus B sub I S VS. And that comes from the fact that the set of all the VI's spans L as a K vector space. So Eleanor, what are we going to do with this?
Put them together.
Put them together and what do you got? Bippity boppity boo.
Exactly.
Thus, you can write M as being equal to, oh gosh, B11V1 plus dot 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 plus B1SVS times M1 plus dot 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 plus B sub R1 V1 plus dot 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 plus B sub RS VS M sub R. And technically I should multiply all of those out and add them together, but can everyone just agree that, is everyone okay if I just say which is a linear combination of the elements of S?
S.
Thank you. Jonah, I don't want to hear otherwise from you. With scalars coming from K. Boom! So we got a spanning set. We got that's linearly independent. We have proven our claim. Okay. Well, now we're basically done, because now we just need to say, since S is the basis for M is a K vector space, well, what's the dimension of M over K? That's just going to be the number of elements in our basis P. How many basis elements do we have?
R times S.
Yeah, because there's R possibilities for the M terms, S possibilities for the V terms. So if you multiply them together, you're going to get R times S terms, which lo and behold gives us what we want. The degree of the extension M over L times the degree of the extension L over K. Bit of a technical result, but basically saying, nice thing. Questions, comments, concerns?
Wait, so when it's a linear combination of elements of S, sorry, what's the S thing?
S is the M sub I, V sub J.
This set right here. Yeah. I gave this set a name because I didn't want to have to keep referring to it as that set over there.
And that's different from the other S, right?
There's another S. Oh, this is a lowercase. This S is this is a lowercase S referred. Okay, maybe. Does that make you feel better?
When in doubt, give it a hat.
Yeah, this S refers to a number, which is just the number of elements in this basis. This S is supposed to refer to this whole set that we proved is a basis for N as a K vector space.
So we should just start using Greek letters.
No, but you don't want to name that capital sigma, because that gets way.
Turns out, if you want to do this over the infinite case, you can do this in the infinite case too, and it's mostly the same argument. You just have to account for the fact that you could have infinitely many of these terms, and when you take a polynomial of them, like all but finitely many of the coefficients automatically have to be 0 to start with. Which is sort of a technicality I just didn't want to get into because it's mostly the same as this, but this is already messy enough.
Why do all that first thing? But because polynomials can't have that.
Yeah, because in a polynomial ring, even if you have infinitely many powers, like this, for instance, is not an element of that.
Oh, what?
You can't have power series be an element of the polynomial ring.
Oh.
You can, if you really want to have fun,
What?
do that, and that just means you allow for power series where you do have infinitely many non-zero
What?
Why?
terms.
Excuse me.
And maybe we'll even do that in a month's time. Who knows?
What?
Yeah, but what if you do R composite?
Lydia, I just blew their mind. You couldn't see it, but trust me, it was mine.
Oh, she could hear it.
Yeah, but what if you do
Didn't see the notation.
well now I don't remember the word, but what if you do R in composition? What is it called? Is it composition? What is it when you use an element that's outside of this? Adjoin it, yeah.
Oh, adjoined.
Yeah. Well, what if you do R adjoined with the power series?
Oh.
R adjoined with the power series?
Yeah.
Really, that gets.
So you want like what? Like, okay, you get that set? I don't.
In that case,
Do you want like polynomials over that set? So are you trying to do something like?
yes.
That
like
guy.
this or something? Because you can do that.
Oh, that sounds.
I don't want to, but you can.
That sounds really fun.
Yeah.
You
All right.
should-
You know what? I'll make a homework problem about
Yeah.
it just for you then.
Want to be graded for it?
Okay. So this theorem that says that equals that. Some of you were mentioning that looks familiar.
Yeah.
What does that look familiar from?
From when we were working with quotient groups and cosets.
Oh yeah. Yeah, when we were talking about quotient groups and cosets, I think I gave this. Those of you who had me in the fall, I think this was a homework problem. At one point, was proving that, like if
Yeah, I think it was.
something like if K is a normal subgroup of L is a normal subgroup of M, then the number of cosets that K has in M is equal to the number of cosets that L has in M times the number of cosets that K has in L.
Yes.
Yes.
Ain't that
I think
fascinating?
that's sweet.
It's
It's probably not related.
related.
No, probably
No,
not.
it can't be related.
That's a coincidence.
And it couldn't possibly be the case that if I had actually made you prove this without using Lagrange's theorem, the proof would look very, very similar to this.
Oh yeah, because we did use Lagrange's theorem.
Lagrange.
I'm a Kentuckian, so I grew up calling it Lagrange, but I'm no longer a Kentuckian, so less.
Lagrange.
So that's all missing. Let's have some fun playing with some examples. Like, how are we doing? Yeah.
I go on. Lagrange's theorem.
There.
I think that's what, no, that's not it.
One for you.
One for me.
Two for you.
Today is
For
the
you.
Dude, I love
27th.
Lagrange.
And Lydia, you know where to find yours.
Is today the 27th? Yes.
Yes, because Thursday is the 29th, and that's going to be weird.
Oh, yeah.
All right, on that. All right, so actually computing the degree of a field extension, as we've seen, can kind of be a pain sometimes.
But if we can just split it up into small.
Well, if we can split it up, then yeah, well, ifs and buts are some. I don't know what I'm trying to say.
Maybe enough.
It'd be nice if we had an easier way to determine the degree of a field extension. And what we're going to be doing in this packet is we're going to be looking at another way of defining degree of a field extension by saying the degree of a field extension is equal to the degree of some polynomial.
Whoa.
And we're going to have a theorem at the end of this packet. Emily Rose, you can look at it. I won't mind. We're going to have a theorem at the end of this packet that literally has 10 things we need to prove.
Let's prove this behemoth of a theorem.
Yes,
Oh, wow.
that's that theorem. But first, let's build up some intuition. So we've seen some rings now. In general, whenever you say something like this, what do we mean? What do I mean? Someone from this side.
Rational number plus a rational number times a.
Rational number plus rational number times a.
Yeah, but what if
If
A,
it's squared until a to the n is rational.
yeah. Until QA something is in the set of rationals, I guess. Unless it never is, I don't know.
Oh, indexing at 0.
Well, I mean, it's the constant term, so the degree 0 term.
Computer scientist time.
Yeah. Where, what do we have to say about the q sub i's?
They're not 0. No, wait, they can be 0.
Well, where do they live?
Oh, they're in Q.
Yeah, the q sub i's all have to be elements in Q. And
This was supposed to be terminating at some point.
Wait,
Doesn't it? Why?
We just.
Q as join X is what?
all,
But finite is not.
Oh, or 0.
because we want to avoid power series like over there.
oh, that's like,
We
Yeah.
just talked about this.
Yeah.
Yeah. If I put more double brackets around it, then we would eliminate this condition. So, for instance, Q join square root of 2. Think of this as being the polynomial ring where your indeterminate has the form A and your coefficients are coming from Q. So you see this ring, I want you to think polynomials of A. So, when we do this, for instance, what are we going to get? We're going to get A plus
Square root of 2 times
plus B square root 2 plus C square root of 2 squared plus D square root of 2
That's
cubed
you gotta fix that, man.
plus that. Oh wait, but this is already rational. This is, well,
You gotta-
rational times square 2D square root of 2. So really, we don't need these terms.
Yeah.
So we only end up with only 2 terms at most.
You gotta stop when it becomes rational.
Yeah. I mean, we don't have to stop. We could have a C square root of 2 squared term, but we don't need to.
You should.
We don't need to. In simplest form, we could just write it in the form A plus B square root of 2.
So what if we wrote it A bar plus B bar
Oh,
root 2?
no.
Where A and B are what?
Well, cause then it, like it.
And like Z mod in, some Z mod NC or something?
Well, no, not really.
We're gonna keep
You could do that.
Cause, yeah,
Well, it wouldn't be, well, then we replace this with
Yes.
whatever Z mod NZ you're
Yeah.
looking at. But yeah, you could do that.
Yeah.
Alright.
but it seems like it's the same kind of simplification that we do with Z mod.
That's true. It's not quite though.
Oh, my son.
But it kind of is.
How about this one? The term's gonna look like in this set. Seamus?
Well, we're going to have A
Very good.
plus B square root 2 plus C square root 3 plus D square root 2 times square root 3.
Just say square root 6.
Or don't.
No, actually, I like it the way Seamus said it. To make it a point that you're to make it clear, like where the square root of 6 is coming from. Technically, you would also need a plus E square root of 2 squared square root of 3 plus F square root of 2 square root of 3 squared plus G square root of 2 squared square root of 3 squared plus, and have infinitely many more terms. Or you could have whatever power you want on the square root of 2 and the square root of 3 terms. But something like this is equal to something like this, so we don't need it. Something like this, no, something like that no, yeah, I had it right the first time.
You had it right first.
That, something like this is equal to something that looks like that, so we don't need terms that look like that. Something like this already looks like something like this, so we don't need it. And it turns out, that's all we need. Questions, comments, concerns? So, same thing, I'm gonna replace square root of 2 with pi.
Woo. Oh,
Oh my goodness gracious.
so that's what it means to have finite.
Yeah.
Not zero.
But is it like arbitrary finitely linear or what?
Yes.
We're gonna have A, we're gonna have B times pi,
Nice.
Plus C times pi squared. Plus D times pi.
actually,
Oh, for that.
I'm gonna run out of letters here otherwise.
Yeah, A through pi to
Are we gonna need all possible powers of pi this time?
Yes.
We are. Because pi, unlike square root of 2 and square root of 3, if you keep multiplying by pi, you're never gonna loop back around to something being rational. From the fact that pi is transcendental. If pi was not transcendental, hint, we're gonna define transcendental in the packet after this one, and it's gonna come, and it's gonna be equivalent to this fact. Actually, proving pi is transcendental takes a little bit of work.
If it didn't loop back around, then you guys had to like turn it into a square root or into a root thing.
Exactly. Basically, pi would be the root of some integer polynomial, and that would be sad. Well, it would be sad. It would be sad in the sense that, like, that would call into question like all irrational numbers, or all irrational numbers algebraic, and we'll get into that. So the A sub I are elements in Q, and all but finitely many of these terms are 0. We don't want infinitely many powers of pi in a single element of this set. There is no upper bound on how many powers of pi you have in an element in this set, but a single element in this set can't have infinitely many powers of pi, if that makes sense.
Just arbitrarily.
Arbitrarily many, sure. Alright, question time. These are all rings. They're all integral domains, in fact. But which of them are fields?
I think the first two are fields.
You think the first two are fields, but not the third one?
I think so, yes.
Why do you say that?
Because I can multiply, well, I can't divide by square root of 2, but I can multiply by square root of 2 divided by 2.
So it turns out if you have some a plus b square root of 2, does this thing have a multiplicative inverse? Meaning, can you necessarily multiply that by rational times rational square root of 2 to get 1?
I think it does because you can multiply by a minus b square root of 2 and then divide by the appropriate number.
Yeah, we're going to multiply by a minus b square root of 2 over a minus b square root of 2. And that'll give us, what, a squared minus 2b squared?
Or not 2b squared.
That is a good question. Divided by a minus b square root of 2, which is, where am I going with this?
I'm not sure.
I'm not sure either.
Because you're looking for an inverse.
I'm
So
looking
why
for an
not just
inverse.
why are you dividing by a minus?
Yeah, I want to multiply this times some c plus d square root of 2 in order to get 1.
I think we confused.
But we can take 1, but we can always
So you
take
multiply
1.
by
Alright, here's what we're doing. We're doing this, and then we need to show that that can be written in the form quotient, rational number, excuse me, Parker, times plus rational number times square root of 2.
Adopt my language, so you know it's right.
Well, we can do that. Okay, this is what I was trying to do.
yes.
By multiplying that by a minus b squared root of 2 over a minus b squared root of 2. Which is going to give us a minus b square root of 2 over a squared minus 2b squared. Shut up. Which is going to be equal to the rational number a over a squared minus 2b squared plus negative b over a squared minus 2b squared square root of 2.
Woo, good job.
Questions or comments on that? Oh, no one's going to ask me what if a squared minus 2b squared is 0? Oh, okay, then I won't ask. Then we won't worry about it.
Dr. Gross, so what if a
Well, no, too late. Don't take backsies.
What if a squared minus 2b squared is 0?
Oh dear, can that happen?
Zero's not a unit.
Yeah. Wait,
Zero's what?
can.
Zero's not a unit, big deal.
It can.
Well, wait, no,
but it
because
doesn't have
we-
to have an inverse.
Well, if a squared is equal, if minus 2b squared is equal to 0, that would imply a squared is equal to 2b squared, which implies that a squared over b squared is equal to 2, which implies that square root of 2 is a rational number. Oh, and that ain't happening. So we don't have to worry about it.
Well, it's a good thing the square root of 2 is an irrational number, otherwise we
Well,
have
square root of 2,
problems.
well, square root of 2 is irrational, then this would just be q, and we would, it would be even simpler to show that it's a field. So this is a field. It's a little trickier to show it, but this is a field. Nellie Rose, you think this one is not a field?
I think it's not a field.
I think it is.
How are we
It's
gonna
not.
divide by pi?
Turns out it's not a field. You can't divide by pi in this range.
It's like the
Because it's
field.
transcendental. Pi and whatever pi you got, you can not divide it.
If it was pi and what now?
I mean, if it was, if
It's
it
like the
had pi
polynomials,
and
but
whatever
they're
pi had.
multiplied by one correct.
So then it would be, what, isomorphic to Laurent polynomials
Right.
over q. Yeah.
And these instances
Then it
are
would be-
like complex numbers, because you can just take the
Yeah.
conjugate of it, yeah.
I mean, note that when adding 1 over pi, you're also adding 1 over pi squared, 1 over pi cubed, et cetera, et cetera.
And polynomials aren't.
And all rational multiples thereof and linear combinations thereof,
It,
etc.
it wasn't, I thought
So-
polynomials weren't fields.
Why is it the case that this is a field, this is a field, that's not a field? That's what we're going to be exploring on Thursday. Hope you all have a good one. When we come back Thursday, we'll start looking at the relationship between the square brackets and the circular parentheses. Turns out, here's the hint. Square brackets, ring. Parentheses, field. That's the short answer.
Can you use this to learn things about open versus closed intervals?
No, because that is an abuse of notation, sir.